We've been talking about indexing, and we've been applying indexing, full text indexing, to strings. So this video, though, is the first in a series where we try to take the things we've been doing with strings and to generalize them to work with graphs. And this is something that people in the field of text indexing worked on for a long time. And there is a formalism called Wheeler graphs, which we'll be building toward, that does a pretty good job of generalizing all the different ways people have suggested for doing this. Okay, so let's get started. This is just a picture of something we're familiar with already, right? So I'm going to show a picture showing the progression of steps involved in taking a pattern, GAT in this case, and matching it against a text where I'm representing the index of the text using this Burrows-Wheeler matrix, right? This is the Burrows-Wheeler matrix, all the rotations in sorted order. And we know that this proceeds in kind of a right to left way. So we're going to start with the shortest suffix that's just t, then we'll match that, and we'll go to the next longest suffix, at, etc. And at each step, what we are finding is the range of rows in the Burrows-Wheeler matrix that have that suffix as a prefix. So okay, so let's start with the shortest suffix, which is just t. So this will be the first range of rows, those bottom three rows, that we'll find. There you go, t. Okay, and so that is the range of rows we'll find in the first step. In the next step, we'll now go find the rows that start with at, the next longer suffix of p. So that's these rows. And in the final step, we'll get the rows that start with gat, and there's just one such row. Okay, we're very familiar with this kind of process. Let's do it again. Same pattern, same Burrows-Wheeler matrix, but this time I'm simultaneously going to highlight in the text where all the candidates are with respect to the text. So instead of just drawing a box around them in the matrix, I'm going to take those same characters and highlight where they are in the original text. Okay, so let's start with the shortest suffix of just t. We saw, this part of the picture already. T. Here are the three rows that start with t. Well, where are those t's in the text? It's all the t's in the text, so you can just go through the text. All the red characters are all the t's in the text. So those are the t's that are in this box here. Okay, so let's now go to the next longer suffix of at. And here I've highlighted again with the box the two instances of at, but now I am also highlighting in the text the two instances of at, the two substrings that are at. I'm drawing a little line under them just to highlight that these are length 2 substrings I'm trying to highlight here. It's not just that I'm not just highlighting the characters, I'm highlighting the length 2 substrings, at and at. And likewise, I can go to the last step where I've matched GAT, and here is there's only one row that starts with GAT, corresponding to the fact that there's only one GAT in the text T. Okay, so why am I showing you this? I just want to take this string here, and I want to take the first step toward generalizing it to a graph, but it's going to be at first kind of a trivial step. It's just going to help us think about the shift back and forth between strings and simple graphs. So now let me take this text t and I'm going to wave a magic wand and turn it into a graph. A very simple straight line graph. Okay, where you will notice I've got nodes and I've got edges, and the original string has turned into edge labels. Right, so the edges are each labeled. The edges in this straight line graph are each labeled with a character from the original text in order, left to right. Okay, so the edges are pointing in the left to right direction with respect to the original text. Okay, so now having done this, I'm just going to return to the same example where I'm going to highlight the rows beginning with increasing suffixes of p in the matrix, and then I'm also going to highlight them in the graph. So let's do that again. So let's start with t. Okay, there's all the rows that start with t. And now I'm also highlighting the t's in the graph, which means I'm highlighting these three edges. Those are the three edges that have t as their label. Okay, Now I'm going to move on and do AT. And now here are the two paths, you might call them. You know, this is here's the A and the T, and I highlighted the node in the middle as kind of like a way of showing that really the edge and the next edge and the node in the middle is like the part of the graph you would sort of have to walk along to spell out AT. And likewise here, this is the part of the graph you would have to sort of walk along to spell out AT. Kind of equivalent to before when I was just underlining the substrings of the string. Okay, same idea. And now here's the next longer suffix GAT, and that's over here. So all of this is just to say that when we were tracking where these substrings were with respect to the string T, just by highlighting the substrings, once we shift from thinking of it as a string to a straight line graph, instead what we're tracking are little paths through that graph. Okay, so we have two interpretations of what we're doing when we're going through this matching process. We're either matching substrings in a string, we're trying to find the substrings in the string that match our query, or we're matching paths in a graph. We're trying to find paths in the graph that match our query, which is to say the concatenation of the edge labels in that path match our query. Okay, let's go to a property that we're very familiar with, right? When we said that we could use the Burrows-Wheeler transform to perform matching, we said one of the properties of the Burrows-Wheeler matrix that enables this is that rows with the same prefix are consecutive because all the rows are sorted in alphabetical order. I'm now going to refer to this property as consecutivity, just a new name for a property we already knew, right? The rows in the Burrows-Wheeler matrix that start with the same suffix are consecutive. Okay? And then let's think about how can we see this. This property is most obviously seen by looking here at the matrix and drawing the boxes like we drew before, right? The T's were all in a row, the AT's were all in a row, the GAT's, there was only one, were all in a row. It's easy to see that property with respect to the matrix. How do we see that same property but with respect to the graph? Well, okay. We're talking about the Burrows-Wheeler order here. When we say consecutive, we mean with respect to this Burrows-Wheeler order, the sorted order of the rotations. So let's take that order, the Burrows-Wheeler order, and put it into the graph somehow so that we can see the Burrows-Wheeler order in the graph. And so what I would suggest is let's just think of all the rows as being numbered 0 through 8. And let's take this first row, right? This 0 is kind of labeling that dollar sign, right? That 0 corresponds to the rotation that starts with dollar sign. So what I'm going to suggest we do is let's just take the 0 and put it into the node that's just before the dollar sign, right? So here's the dollar sign. This is the character we're talking about. This dollar sign is this dollar sign. We're going to take that 0 and put it into as a node label. We're going to label the node just before the dollar sign with the number 0. Okay, so there's that first row. The second row, we're going to do the same thing, except we're going to do it with this A. Which A is that, by the way? Okay, let's look at it in the context of that row. A, C, A, T, dollar. So looking backwards, it's this A, right? So this number 1, labeling this row, starting with this A, we're going to just copy it in as the node label for the node just before that A. And likewise, now this A that we're going to do next is this A here. So the 2 is going to go right there. And now this A is the A at the beginning, this A. So we're going to put a 3 right here, etc. I'm actually going to fill all the rest of them in. Okay, so there, I did it for 0, 1, 2, 3, 4, 5, 6, 7, 8. And now the nodes are labeled according to the Burrows-Wheeler order. Okay. Now that we've done that, we can talk again about consecutivity and what consecutivity looks like in the graph. So let's say we've done a little bit of matching and we're at this point where we've matched the suffix AT, right? So that corresponds to a couple of paths through this graph, and we can highlight them. sort of the same way we did before. So that path and this path, right? And what we notice is that for those two paths, the node that's at the head of the path, right, that's just before the path, that those two nodes are labeled 2 and 3, corresponding to these two labels, 2 and 3, and those are consecutive. 2 and 3 are consecutive. And so this gives us an indication of how we can see consecutivity in the graph, right? Basically, at any given point when we are tracking the paths that correspond to the match so far, if we look at the node labels for the nodes that are just prior to those paths, that are just at the heads of those paths, those will be consecutive. Okay? So in this example, again, we have 2 and 3, we have 2 and 3 as the row indexes for these two rows that start with AT. Likewise, for the two paths that match AT, the nodes just upstream, the nodes at the heads of those paths have labels 2 and 3, and those are consecutive. Let's just, as another example, let's do the T's, right? This is from the first step of the matching process. We would get those 3 rows. Let's look at the graph again, and let's look at the 3 T's, right? So we're actually looking at this path and this path and this path. And what we notice is that 6, 7, 8, 6, 7, 8. So again, the nodes at the heads of those 3 paths have labels that are consecutive, 6, 7, and 8. Okay, so node labels in a Burrows-Wheeler range are consecutive. It's hard to see, like we have to jump back and forth. You know, we have to draw the paths in the graph and then look at the heads of the paths and then look to see what their labels are, and that might require looking all over the graph. So let's make it a little easier on ourselves by just taking the graph and reordering the nodes so that not changing the graph in any way except drawing it differently, where the nodes are in order according to these labels that we gave them. So again, let's show this is our same graph. For completeness, I've drawn an edge that goes from the final node back to the first one, and to represent that these are rotations. And now all I'm going to do is I'm going to draw that same graph, but I'm going to draw the nodes in this order. Right? So how do I draw the same graph now? Well, okay, let's start over here. Let's think about this node, the node labeled 0. Let me transfer over its outgoing edge, the one that's labeled $. Okay, so up there, the outgoing edge labeled $, goes to node 5. So let me add an edge like this, and give it the label $. Okay, so that's so far so good. So now, okay, so now we're at 5. So let's think about the outgoing edges from 5. So there's one outgoing edge, and it's labeled G, and it goes to node 3. So let's draw that one in. Like that. Here's our G. And so on. So I can do this now outgoing from node 3. I see an edge labeled A going to node 8. So let me do that one. Okay. And it should be pretty clear I can do this for the entire diagram, right? It's exactly the same graph. I've just relaid it out so that the nodes are in ascending order by their labels left to right. Okay. So now if I go through that same process where I want to know what are the nodes that are at the heads of the paths for when I've matched a certain string, well, now it's pretty clear, right? So like, let's take those same nodes that we had before, right? So we had 2 and 3, right? Because again, looking up here, 3 is the one that has AT after it, 2 is the other one that has AT after it. So now 2 and 3 obviously are right next to each other, right? As opposed to being far apart from each other, right? Simply because we've reordered the nodes. So consecutivity now means that the nodes that are at the heads of these runs are all going to be next to each other. Okay, likewise for 6, 7, 8, that was the other trio. because those are the ones that are just upstream of the t's. 6, 7, 8. So whereas up here they're kind of spread out, down here they're all right next to each other because that's the order we put the nodes in the diagram. Okay? So all we've really done is we've come up with kind of a graph way of writing, essentially, the Burrows-Wheeler transform, right? So the original string would be written like this. What we did when we reordered the nodes in Burrows-Wheeler order was to write the nodes in basically that same Burrows-Wheeler order that we would have permuted the characters in, applying the Burrows-Wheeler transform. A little bit more about this now. So let's stick with the graph as we've drawn it here, with the nodes in ascending order by Burrows-Wheeler row. And let's think of the nodes in two different ways. Let's think of the nodes according to what is the label of the edge going into the node. And separately, let's think of the nodes according to what are the labels of the edges going out of the node. And when I say edges, I mean the path of edges going out of the node and to the $, basically. So like if we follow edge, 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 edge until we get to the $, what's the label that we see along the way? Okay, so here are those two ways of thinking, after and before. Let's start with the before. Okay, and just look at the nodes that we have here and just write down, I'll just draw like a little line down here, and then down here I want to write what's the label of the edge that's incoming, that's incident to that node. Well, looks like it's T, right? It's this edge right here, and that's labeled T. So I'm going to write T right here. Likewise, what's the label of the edge incident here? It's another T, right? Right? T. How about this one? It's a C. How about this one? It's a G. How about this one? It's an A. Keep going. How about this one? It's $. How about this one? It's A. This one is T. This one is A. But that's just the Burrows-Wheeler transform, right? That is the Burrows-Wheeler transform of the original string. It's just the label of the incoming edge onto that node, right? The label of the outgoing edge would correspond to the first column of the Burrows-Wheeler matrix. But the label going into the node corresponds to the last column of the Burrows-Wheeler matrix. So if we just look at the labels of the incoming edges on each node, that's the Burrows-Wheeler transform. Okay, now let's think of the edges outgoing from the nodes. Not surprisingly, what we expect these to spell out, let's say we stop at the $, right, just for convenience. So what we expect those paths to spell out are the suffixes, the suffixes, basically the rows of the Burrows-Wheeler matrix up to the $, right? So the node labeled 0, what we expect to see on the edges leaving that node is we expect them to spell out that first row of the Burrows-Wheeler matrix. And we'll stop at the $. And lo and behold, of course, the first row is just a $, right? So the $'s first. So let's just call the suffix $. Okay, let's look at the second one. This is going to correspond to what's the string in the second row of the Burrows-Wheeler matrix. So let's just spell it out by following the edges. Okay, outgoing edge is labeled A. So we have A, C, A, T, $. ACAT $. Next one, node labeled 2. Again, let's follow the edges. A, T, $. It's a nice short one. Again, what are we doing? We're just spelling out the rows of the Burrows-Wheeler matrix. That was the third row, stopping at the $. Okay, now let's go with the node labeled 3. We have A, T, T, A, C, A, T. A, T, T, A, C, A, T, $. And so on. Right, you can see what I am doing. I am spelling out right? I've got them diagonally here, but if you just sort of put them upright and stack them on top of each other, you would be seeing the rows of the Burrows-Wheeler matrix, but stopping at the dollar sign. Right? We didn't have to stop at the dollar sign, but we know what would come after that, right? You know, here we would have the whole string. Right? We know what comes after the dollar sign. Right? I'm just not drawing that. I'm just drawing up to the dollar sign and then stopping. All right, so those outgoing paths, right, as we walked along the path outgoing from a particular node, just concatenating the edge labels together, we were spelling out a suffix if we stopped at the dollar sign. Or if we didn't stop at the dollar sign and we kept going till we came back to where we started, we would have got a rotation. Okay. So the incoming edges, the incoming edge labels correspond to the final column of the Burrows-Wheeler matrix, which is to say the Burrows-Wheeler transform. The outgoing paths from the nodes, if you follow the path, you're spelling out a suffix or a rotation. And so those are in order, right? Because if this is the Burrows-Wheeler order, then what you're getting are the suffixes or the rotations in alphabetical order. Okay, so the next question, which we'll just start to answer in this video and then answer in more detail in the next one, is can we go beyond these straight line graphs? Right? We've created all these connections where we've said, oh, well, we can think of a string as a straight line graph, and we can think of matching substrings as matching paths in the straight line graph, and we can think of consecutivity with respect to the Burrows-Wheeler matrix as consecutivity of the indexes of the nodes at the heads of the matching paths. But all of this is just sort of a little game unless we can actually generalize to graphs that don't correspond to strings, that are more complicated than just straight line graphs. So for example, let me show you such a graph. So here's one. Here's a graph. What do you think it means? You know, it's not a straight line graph anymore. So again, it doesn't really correspond to a string. So what does it correspond to? Well, okay, there's still a direction to the edges, so that's kind of helpful. We kind of can appreciate that we're going to have to read this left to right. It's just that we get to here, and then there's kind of like a choice, right? I can go this way, or I can go this way. And you start to get the idea, well, there's only two distinct ways of getting from the left to the right end of this thing. Maybe this basically corresponds to two strings, right? The string I would get if I walked along and went up, and then the string I would get if I walked along and went down, right? And those strings have a shared prefix and a shared suffix. So let's just write them down. So one of them would be G, A, T, T, going along the top, A, and I'm going to draw a C, and I'm going to draw it in purple, because this will be where the two strings differ, as you'll see. And then keeping on going after this sort of join point here, right? A, T, dollar. Okay, now let me do the bottom. G, A, T, T, A. Now G, there's a difference there. A, T, dollar. Okay, so why did I use purple? I used purple because that's the position where there's a difference between the two strings. And you might be wondering, we won't see the answer to this question yet, but why I didn't do something simpler. Like you could have imagine I'm now drawing an alternative version of this part of the graph. So we could have that incoming edge labeled T, and then this edge labeled A. Instead of splitting, I don't split. And then I could have another node here, and there would just be two different edges from this node to this node, one of them labeled C and one of them labeled G. And then there'd be the outgoing edge on A. You might wonder why I didn't draw it that way. That's going to have to remain a mystery for now. We're going to actually get from this graph to the notion of Wheeler graph, and I wouldn't be able to do it if I'd drawn it that other way. So I'm sorry, but that's going to have to remain a mystery. And so the question we're going to start the next video with is, do these ideas that we had about the two different ways of thinking about the nodes still hold, right? So we had one notion, which is that a node can be thought of as what's the label of the incoming edge, and this ended up corresponding to the Burrows-Wheeler transform if we put the nodes in that order. And then the other notion, which was that we could think of the nodes in terms of what's the label of the path leading out from the node going to the dollar sign. And it's going to turn out that we're going to have trouble generalizing both those notions, but it's still going to be possible, and we'll see why in the next video.